We will be explaining the topic of friction, moments, and the instantaneous center of zero velocity and how they relate to wheels. The scenario we will be examining is a bike accelerating forward without slipping. To understand how friction and moments of the wheel work, it is important to first understand the instantaneous center of zero velocity.
We can find the instantaneous center of zero velocity by analyzing the velocities at each point on the bike wheel. We know the bike wheel is rotating without slipping and moving to the right. To find the instantaneous center of zero velocity at point C, we know point C must lie on the same line as, for example, point A, which is perpendicular to the velocity at point A. This is true for point C and any other point on the bike wheel. The reason this is true is because velocity equals the cross product of angular velocity and the radius, also known as omega cross r. For example, in this situation, the omega of the bike wheel is in the negative k-hat direction, and the radius of A relative to C is in the positive i-hat direction. A negative k-hat crossed with a positive i-hat results in a positive j-hat, which corresponds with our diagram. This is a long exposure photo of the light attached to the bike wheel. By tracking a single point on the wheel with the light, we can see that a cycloid shape is produced. The photo shows that at the point of contact between the bottom of the wheel and the ground, there is zero velocity. In these videos, we attached a light to the bike wheel in order to better see the motion of the bike wheel.
To find the frictional forces of the bike tires, we have to look at the impending relative motion of the contacting surfaces. As we can see in the diagram, only the back tire has an applied force. This is from the bike's chain. We can assess impending motion by considering the wheel on a frictionless surface. In this case, the wheel would simply spin in place. Thus, the impending relative motion of the contacting surfaces is the wheel moving to the left relative to the ground at the point where the bike wheel touches the ground, and therefore friction is to the right. On the other hand, the front tire's impending relative motion is the wheel sliding to the right relative to the ground. Thus, the front wheel's friction force is to the left. We will now look at the moment and direction of the rolling wheel. Since the back tire is being pulled by a force caused by the chain, we will focus on that one. We want to find the moment of the wheel, so we are only going to look at the FBD. Moment is equal to R cross F. In this case, our R is in the positive j-hat direction, going from C to our center of gravity, and our F is in the positive i-hat direction, to the right. Therefore, M is in the negative k-hat direction, and thus the wheel rolls clockwise.
We hope this video helped you understand the motion, friction, and moments experienced by wheels that aren't slipping, and how the three topics are related. Thank you for watching.